All right. So last week on Friday, we did some exploring, and we learned that there is an inverse to exponential functions, right? So our exponential function was a one-to-one function, which means that every input has exactly one output, and that is one of the criteria for finding the inverse of it, right? And we talked about the inverse, how the graphs are reflections of each other over the line y equals x. We switch the domain and range, right? So those properties give us another specific function, which we call a logarithmic function. So here we have just some kind of formalities to get out of the way. So again, we have the inverse of the exponential function a to the x is the logarithmic function with base a. So there is a key distinction there, all right? Here we're talking about specific bases, right? So that's a key part. So just like our exponential function, we're looking at values of a that are positive and not 1, all right? If it was 1, it wouldn't really work. So here we have a direct relation between the exponential function and the logarithmic function. Oh, I wrote this wrong. My mistake. Swap this. Sorry about that. All right, so if I have the function y equals log base a, okay, so that's how we say that. All right, so anytime you see this, this is log base a of x. All right, so again, x is our input, or our domain, or our independent variable. Okay, that's the word I was looking for. In this form, you can directly translate it or manipulate it to look like this. All right, so they are inverse of each other. So if you have y equals log base a of x, that's the same thing of saying a to the y power is x. All right, and when we start using some numbers, that part might become a little more clear. All right, but again, the function f of x equals log base a of x. That's how we say it in the quotations there, log base a of x. And we call that the logarithmic function with base a. All right, so let's actually use some numbers, and so we can see the exact relationship between those two expressions. Okay, I think I went over this. Remember that this means if and only if. So both of these parts have to be true, right? So if log base a of x equals y, then a to the y equals x, and the reverse has to be true. Okay, so this just means that both of these are very important parts. All right, so let's take a look at some numbers. So if I said something like 2 to the 5th equals 32. Okay, so I have 2 to the 5th power equals 32. So I'm going to put this up here, actually, y equals log base a of x. A to the y equals x. So all we're doing is we're rearranging our exponent, our base, and our answer. Okay, I keep emphasizing the word base because in both of these, the base is the same thing. Okay, here the base of our exponential function, okay, would be base a. Here is our base. Okay, they're just in different spots. Okay, so if I had the expression 2 to the 5th equals 32, if I wanted to write that as a logarithm, I would have the logarithm base 2 of 32. And that would equal 5. Right? So another way to read or to kind of think about the logarithm is saying what power of 2 gets me 32? Okay, what do I have to raise 2, or 2 to what exponent gets me 32? Well, that would be 2 to the 5th gets you 32. Okay, we use that method to help us evaluate logarithms. So if I said, if I just wrote, what do I want to write? Okay, so if I had something like log base 5 of 125 equals x. So you're saying to yourself, 5 to what power gets me 125? Right? Sometimes it's a little hard to, to think like that. So I would recommend rewriting it. So 5 is my base. My answer is my exponent. And then what I plug into the logarithm is the result. Okay, so 5 to what power x would be 125. All right, so in this case, our solution would have to be 3. All right, so again, it all depends on what base that we're dealing with. Let's take a look at a few more examples. How are you guys feeling about this? Is this kind of catching on, or is this hieroglyphics to you guys?
It's good.
Okay, we'll look at a couple more examples and then we'll go to some basic properties. All right. I don't want to jump to those yet. All right. So if you're asked to do something like this, you'll see it like this. You'll be asked to evaluate log base 4 of 16. Okay, so if you're comfortable enough, right, you can say 4 to what power is 16, right, and you can solve it. Right? If you're having a little difficulty making the connection, okay, what you're going to do is you're going to write equals x or equals y or equals a, b, c, whatever you want. You're going to change it to exponential form. So this is saying 4 to the x power equals 16. And then here it might be a little more clear, right? So 4 raised to the second power is 16. So you can say that the log base 4 of 16 is 2. All right, because 4 squared equals 16. All right, so you can swap it like that. So just be careful though, because sometimes it may not look like it makes sense. Okay, but when you change it to this part, it might be a little more clear. So let's take a look at something like this. Log base 3 of 1. All right, so 3 to what power gets us 1? Now this one's kind of a trick question, but we're going to follow the same steps. All right, so I'm going to set it equal to x. I'm going to rewrite it as a exponential equation. So 3 to what power gives us 1? Now there's only one case where this is true. All right, and if you remember your rules about exponents, your exponent would have to be 0. Okay, anything to the 0 power is 1. All right, and actually I'm gonna bring this up again in a second. Let's take a look at one more example. Okay, let's take a look at log base 4(2). Actually, one thing I do want to say before we move on. If you have to write these out, if you have to do the logarithms, please make sure your bases are smaller and lower than your numbers. Okay, they're known as what's called subscripts. Okay, so whenever you write it, okay, you're gonna do log and then make sure that it's smaller and lower than it, and then whatever number you have here. Okay, because if you write something like that, that doesn't really make sense. Okay, and actually this kind of means something different than what we're talking about. All right, so log base 4 of 2. So here we have a smaller number than our base. All right, so this is saying 4 to what power gives us 2. All right, so when we have this, now remember, there's a few things going on with our exponents. Well, our answer isn't a fraction. Okay, if our answer, or if our input here, okay, was a fraction, well, to get a fraction from an exponent, we'd have to be negative. So it's not going to be negative, not yet. But what can I do to 4 to get to 2?
Divide.
In terms of, okay, so right, we want to get smaller. So is there division anywhere going on here? That's a good point, right? 4 divided by 2 gets us 2. But with logarithms, we don't show division. We can only show exponents. So what's another way of getting from 4 to 2 other than dividing? Other than our basic operation. So no subtraction, no dividing. How can I get from 4 to 2? When I say it, you guys will be like, oh, yeah. There we go. Okay, we're going to, well, if we square 2, we get 4. So going in the opposite direction, what's the opposite of squaring? We're on the right track. Right, the inverse of squaring gets us a bigger number. If we want to do the opposite, we're going to square
root.
Okay, so how do we show that? Okay, so remember, if I had the square root of x, I can write that as an exponent as x to the 1/2. All right, so here my exponent would have to be, that's a real sloppy too. Our answer would be 1/2. All right. Actually, let's do one more, just because I do want to bring up what I said before. Okay, I want to evaluate log base 10 of 1 over 100. So here we have a fraction. Okay, so actually, before I go on, we could have solved this using what we did last week, right, with our exponents. 4 to the x is also 2 to the 2x, right? If we find a common base, and then this would be 2 to the first. And then looking up here, I have 2x equals 1, or x equals 1/2. Okay, so you can always fall back to that, that algebra way of solving if you get stuck. All right. So here, I want to know 10 to what power gets me 1 over 100? Well, I can rewrite this 1 over 100 as 100 to the negative first, right? Anytime we have a fraction, I can bring it to the numerator with a negative exponent. Well, then 100 we know is 10 squared. So our answer here would be -2. Okay, this actually brings me to something I want to talk about next. So on your calculators, on a very basic calculator, you don't have all these options, right? You can't calculate log base 2, log base 4, or log base 3. What you see on your calculator, okay, is just, that's kind of a little fuzzy probably, but that just says log by itself. Okay, that's known as the common logarithm. Okay, the common logarithm is a logarithmic function with base 10. Right, so if you had log base 10 of x, you can just write that log of x. So anytime you're evaluating a function, or if you're graphing a function or anything from here on out, if you don't see a base, there's an invisible 10 there. All right, so with that, okay, you actually, you can actually calculate anything with log base 10. Again, on your calculators, when you turn it to landscape mode, you will see a log button there. Usually it's next to the exponential one. All right, it's somewhere in that vicinity. So you just see log. All right, we call it log. All right, and that is known as the common logarithm with base 10. All right, so just moving on forward. All right, so last thing I'm going to leave you with today is a few rules, okay, some basic properties. So these are true about any logarithm. So I'm just going to use base A, so because it doesn't matter. So the first one we actually just saw in one of our examples. No matter what our base is, if we're taking the log of 1, the answer is 0. Right? And that's always because anything to the 0 power is 1. Right? So it doesn't matter what number's here. You could be the common log of 1 is 0. It could be log base 5 of 1 is 0. It could be log base 1,000 of 1. That's 0. Okay. Again, remember, A always has to be positive, so you'll never see a negative number down here. Right? It doesn't make sense conceptually. Our second rule, if we are taking the logarithm and that number is the same as the base, that's always going to be 1. And that's because anything raised to the first power is always itself. All right, so if you had log base 5 of 5, that's 1. Okay. Log of 10 is 1. Okay, our common log. Like our exponential rule, okay, because we have the one-to-one property, as long as I have the same bases for my logarithms, okay, then what's inside them is going to be equal. All right, we'll look at this a little more tomorrow. All right, but if log base a of x equals log base a of y, well, then x has to equal y. Okay, and that's, again, using our one-to-one property like exponentials. And then our last rule Okay, the last rule is how we use logarithms and exponents together as inverse functions to solve. Okay, so like if I had 2x equals something, I would divide by 2 on both sides because that's the inverse property. So here, if you have log base a of an exponential function a to the x, well, all of this eliminates and all you're left with is the x. Okay, and the reverse. If you have some a to the power of log base a, well, again, those two are going to eliminate each other, and all you'll be left with is your value of x. Okay, these two we're going to go more in depth tomorrow. Don't worry about those two too much. Okay, any questions about logarithms? I know this is probably, some of you may, messing around with your calculators or in Algebra 2, it may have been mentioned, but this is a fairly brand new topic. Okay, so tonight I'm going to give you a few problems where I want you to evaluate. Okay, so there'll be like these examples that we went over today. And then tomorrow we'll get into actually, solving stuff and using them algebraically. And well, we already took a look at the graphs, or the basic graph. We'll look at some more graph stuff later on, later on in this week as well. All right. So that's all I got for you guys today. No other questions, then have a great day. Keep an eye out for the assignment, and I'll see everybody tomorrow.
Thank you, you too.
Thank you, you too.